Dawn, August 19, 1942. Before the sun fully rose over the French town of Dieppe, the Allies were already marching toward a disaster no one saw coming. What happened in the next few hours would stain the beaches red and rewrite the entire strategy for invading Europe. Operation Jubilee was sold as a recon attack, a quick strike to test German defenses and prove a port could be taken by force. But the moment Canadian troops hit the shingle, it became something else, a lesson in everything that could go wrong in an invasion. Machine gun fire raked the beaches. Artillery found the landing craft before they could even unload. German bunkers sat high above the harbor, covering every approach with overlapping fire. By the time the shooting stopped, almost 4,000 of the 6,000 men who landed were dead, wounded, or prisoners. But the real lesson of Dieppe wasn't just the bodies on the beach. It was the ports. For years, Allied planners believed one thing: you cannot invade France without capturing a working harbor. Tanks, trucks, fuel, ammo. An army needed tens of thousands of tons of supplies every single day. You couldn't dump that on open sand. You needed cranes, docks, warehouses. And Hitler knew it. From Cherbourg to Calais, every major port had been turned into a fortress. Concrete bunkers, naval guns, thousands of troops. The so-called Atlantic Wall was growing into the most powerful coastal defense system on Earth. Any assault on a port would end exactly like Dieppe, a slaughter. That left the Allies with an impossible equation. You need ports to invade. You can't invade without ports. And even if you captured one, the Germans would blow it to pieces before retreating. Reports from occupied Europe showed the same thing again and again. When the Germans pulled back, they destroyed everything. Cranes, docks, locks, channels, ruined beyond use. If the Allies did land, their armies would starve on the beaches before engineers could rebuild anything. The math was brutal. A modern force needed 40,000 tons of supplies a day. Without a port, invasion was suicide. Throughout late 1942, Allied planners circled the problem like a maze with no exit. No one could find a solution. Traditional engineering had nothing to offer. The Allies didn't just need a port. They needed a new kind of port, one that could appear instantly where none existed. And the idea came from the strangest place, a dusty memo Winston Churchill had written back in 1917. During the First World War, Churchill had proposed something that sounded insane even for him. Artificial floating harbors, giant concrete and steel structures that could be built in Britain, towed across the sea, and turned into instant ports anywhere in the world. The Admiralty had quietly shelved it as impossible. But Churchill never forgot. And on May 30th, 1942, just months before Dieppe proved him right, he sent an order to Lord Louis Mountbatten that cut straight to the point. Build floating piers for beaches. They must rise with the tide. Solve the anchor problem. No arguing. Make it happen. It sounded reckless. It sounded crazy. But it was the only path left. Naval officers laughed at the idea. Engineers shook their heads. The English Channel was too rough. The structures too big. The tides too violent. The materials too massive. The tow distance too long. Everything about it broke the rules of harbor construction. Ports were built on solid land over years, not floated through storms under enemy fire. But Churchill understood something the skeptics didn't. War doesn't care about what's possible. It only cares about what you must do to win. Dieppe had proved one thing with painful clarity. If the Allies couldn't capture ports, they had to bring their own. Mountbatten knew conventional thinkers would never attempt it. So he turned to a man with a rare mix of courage and imagination, Captain John Hughes Hallett, a naval officer, a rebel, and someone who had seen the Dieppe disaster up close. And he had reached the same conclusion. Stop trying to seize ports. Start building new ones. His first move: ignore every traditional engineer the War Office tried to assign him. Because he didn't need men who knew how harbors should work. He needed men who could imagine how harbors might work under impossible conditions. And that decision would change the entire future of the war. And that unusual team, the one built on imagination instead of rules, was about to grow even stranger. Their first major recruit was Bruce White, a civil engineer who had spent years building docks across South America. If anyone understood how concrete behaved in seawater, it was him. At first, Bruce thought Hughes Hallett had lost his mind. Floating concrete blocks weighing thousands of tons? Ridiculous. But then he ran the numbers. Concrete didn't need to float like a ship. It only needed to displace more water than it weighed. Hollow concrete boxes, called caissons, could do exactly that. He'd seen small versions used as dock gates. Scaling it up would be insane, but not impossible. And that was enough. White joined the project and brought a hand-picked team of concrete specialists with him. Next came Alan Beckett, known for designing the floating pier at Weston-super-Mare. His pier let boats dock despite some of the biggest tides in Britain. The secret: floating roadways on flexible joints that rose and fell smoothly with the tide. When Hughes Hallett saw Beckett's work, he instantly knew it could be adapted for tanks, trucks, and heavy cargo. Beckett arrived in London expecting another seaside pier job. Instead, he learned his new pier had to move 100 military trucks an hour, while under enemy fire. From there, the team exploded in size. Railway engineers who understood flexible roadbeds. Bridge designers who knew how floating structures carried stress. Harbour masters from Liverpool and Southampton. Naval architects who could predict how large objects handled violent seas. Piece by piece, the impossible started becoming a blueprint. The plan wasn't one structure, it was a system. Breakwaters, floating roadways, piers, anchors, and platforms that all connected like giant Lego pieces. And the rule inside their meeting room was simple. No idea gets rejected. If it breaks every rule, good. Then figure out how to make it real. Breakwaters in days, not decades. Sink concrete giants offshore and link them together. Movable piers that handled 20-foot tides? Put them on telescoping legs. Anchors for soft sand and chalk seabeds? Invent cross-shaped anchors that twisted deep into the seafloor. Every impossible problem became a challenge to solve. By early 1943, Hughes Hallett's Misfit Squad had turned Churchill's dream into actual engineering drawings. Now came the terrifying part: building it. Phoenix, the heart of the artificial harbors. The central component was codenamed Phoenix, giant hollow concrete blocks that would act as floating breakwaters. They weren't elegant. They were floating fortresses. The largest were 204 feet long, 56 feet wide, 60 foot tall, weighing 6,000 tons. Basically, concrete office buildings that had to float across the channel and then sink themselves into perfect position. White's team calculated they'd need over 200 of these, in multiple sizes. The engineering problems were monstrous. Standard concrete would crack. Hollow chambers needed to survive enormous wave pressure. The walls had to be thin enough to float, thick enough to endure bombs and storms. White redesigned concrete mixes, thickened the lower walls, and filled the interiors with a maze of compartments to add strength without killing buoyancy. Some even had anti-aircraft guns mounted on top. But the biggest innovation was the construction method. Traditional breakwaters took years, built stone by stone. Phoenix units had to be built like ships, cast in dry docks, floated out, and stored until needed. The concrete was poured in stages, day and night, because pouring too fast caused dangerous heat cracks. Every unit required exact ballast calculations. Float too high, and they'd flip. Float too low, and they'd sink. Crews of 6 sailors would live inside each caisson during towing, managing pumps and ballast like they were operating a submarine made of concrete. Sinking them was a precision ritual. Flooding chambers in the right order, at the right speed, at the right place, to make them settle upright and lock together. A mistake of even a few feet could ruin the entire harbor. Britain becomes one giant shipyard. To build everything, over 200 caissons plus piers, roadways, anchors, and floating platforms, Britain transformed its coastline into the largest construction program in its history. Dry docks, estuaries, and hidden inlets from Scotland to Cornwall became Phoenix factories. By peak production, 16,000 workers were building Mulberry Harbour components. Many weren't engineers at all, just ordinary workers suddenly building the most ambitious port system the world had ever attempted. And they were only getting started. And while Phoenix units were being built at a frantic pace, an even stranger army was forming around them. Tens of thousands of ordinary workers who had no idea what they were actually building. Most of the labor force wasn't made of specialists. They were dockhands, builders, welders, carpenters, and anyone the government could pull from other wartime jobs. The secrecy was total. One site might be told they were building coastal defenses. Another believed they were constructing floating fuel tanks. In truth, all of them were unknowingly helping assemble the invasion harbors that would appear off Normandy months later. The logistics were overwhelming. Cement was rationed across Britain, yet Mulberry swallowed it in unbelievable quantities, enough to build entire towns. Steel reinforcing bars were stripped from other projects. Timber for molds arrived in endless rail convoys. The Thames sites alone consumed 75,000 tons of cement, 14,000 tons of steel, and kept 5,000 workers busy day and night under floodlights shielded from Luftwaffe reconnaissance. Each construction zone became a temporary city, canteens serving meals around the clock, dormitories for exhausted workers, new railway lines for supplies, and medical stations treating crushed hands, broken bones, welding burns, plus the occasional fatal accident. Several men died building Phoenix units, but even their deaths were hidden under the cover of industrial incidents. Secrecy ruled everything. The largest and most extraordinary yard was at Stokes Bay, built specifically for Phoenix production. 6 gigantic caissons could be poured at once inside enormous excavated pits. When finished, the pits were flooded, gates opened, and tugs eased each concrete giant into open water. Soon the Solent was crowded with dozens of floating gray monoliths, silent, mysterious, and off-limits to public discussion. Locals invented rumors, but the truth stayed locked behind military orders. By June 6, 1944, every component was ready. The invasion hit Normandy at dawn, and while soldiers fought inland, the second phase of Operation Overlord was beginning. On June 7th, the first Phoenix units started crossing the Channel. It wasn't a convoy, it was a maritime choreography involving hundreds of vessels towing hundreds of concrete hulks toward France. The crossing was painfully slow. A Phoenix moved at 1 to 2 knots, taking 18 to 20 hours in good weather. Larger ones needed 2 or 3 tugs pulling together. And they behaved nothing like ships. They were floating rectangles that fought the water with every mile. Channel tides could run stronger than the towing speed, so commanders had to time departures with tidal windows and constantly adjust course. If the sea picked up even slightly, the caissons yawed, swung, or threatened to roll. Several broke loose when tow cables snapped, steel ropes thick as a man's wrist that recoiled with lethal force. Some drifting units had to be abandoned. German threats never disappeared. E-boats prowled the night. Luftwaffe pilots made desperate strafing runs, bullets scattering off concrete while small crews hid inside ballast compartments. Yet most units survived. Crews learned tricks on the job, ballasting caissons lower to reduce drag, communicating between tugs with lamps, and discovering that night towing was safer against both weather and aircraft. By the second week, something unbelievable had happened. This insane operation had become routine. When the first Phoenix units reached Normandy, the hardest phase began, assembling the harbors in a war zone. 2 sites were chosen. Mulberry A at Omaha for the Americans. Mulberry B at Arromanches for the British and Canadians. Even with their favorable seabeds and natural partial shelter, they were still exposed coasts watched by German gunners inland. Assembly started with the outer breakwaters. Using divers' markers, compasses, and raw seamanship, teams positioned each caisson in its precise location. Flooding valves opened, water rushed in, and the giant blocks settled onto the seabed in perfect sequence. Within hours, they became permanent coastline. But Phoenix was only one layer. Farther out, engineers anchored bombardones, 200-ton cruciform steel floats that broke incoming waves before they reached the concrete line. Installing them meant lowering 20-ton anchors in deep water while German shells occasionally screamed overhead. The enemy couldn't see the work directly, but blind artillery still landed dangerously close. Inside the growing ring of protection, crews began building the whale piers, Alan Beckett's masterpiece scaled up for war. These were floating roadways supported on telescoping steel legs that rose and fell with the massive Normandy tides. The floating roadway stretched almost a mile offshore to where Liberty ships could unload straight onto the piers. At the beach end, flexible bridge sections pivoted on huge hinges, keeping the roadway stable as the tide swung nearly 20 feet twice a day. Sherman tanks and supply trucks rolled across the early sections even as engineers were still bolting others together. And then, just as the system began working flawlessly, weather officers noticed a worrying trend. On June 18th, barely 2 weeks after D-Day, the barometer began to fall. A storm was coming, and the worsening forecasts proved accurate. By the evening of June 19th, the channel was no longer merely rough, it was turning hostile. Winds climbed past force 6, surging toward force 8, and within hours the seas were heaving into towering walls of white water. What followed over the next 3 days became the defining trial of everything Hughes Hallett's engineers had created. The storm hit with a ferocity no one expected in June. Waves 15 to 20 feet high pounded both Mulberry sites, and crews watched helplessly as the carefully aligned breakwaters vanished under boiling surf. Mulberry A, the American harbor at Omaha, began failing almost immediately. Lighter construction choices made for speed now proved fatal. Smaller Phoenix caissons were overwhelmed, water surging right over the tops. Then the floating bombardones started snapping free of their anchors. Each 200-ton steel float became a drifting battering ram, smashing into the outer walls and tearing gaps the sea eagerly exploited. Once the perimeter broke, the inner harbor was exposed. Whale pier sections twisted apart, pontoons folded under the strain, and their telescoping legs bent like wire. Entire lengths of roadway tore loose and washed ashore. Liberty ships, once sheltered, were battered against concrete or forced to cut loose and run for open water. One vessel was thrown completely onto the sand and left there for good. By the time the storm eased on June 22nd, Mulberry A was finished. A few caissons still sat where they had been sunk, but the harbor as a working installation was beyond saving. The Americans abandoned it and stripped what they could to reinforce the British harbor. At Arromanches, Mulberry B was battered but alive. The British insistence on heavier caissons and tighter spacing, criticized during planning as wasteful, now proved decisive. Though damaged, the main breakwater held. Where bombardones tore free, the massive Phoenix units absorbed the impacts. Within days of calmer seas, engineers had patched enough pier sections to resume steady cargo flow. The wreckage of Mulberry A was towed over to further strengthen the surviving harbor, turning it into a single vast logistical engine. The results were extraordinary. From June 7th to the end of October, Mulberry B moved more than 2.5 million troops, 500,000 vehicles, and 4 million tons of supplies. More than Britain's busiest peacetime port handled in a year. At peak output, over 7,000 tons per day came ashore over its floating roadways. It outperformed every captured French port. Cherbourg, taken on June 27th, was a ruin requiring months of clearance. Le Havre contributed almost nothing in 1944. Meanwhile, a man-made harbor on an open beach was keeping the Allied armies alive. The strategic impact was staggering. 4 decades military doctrine insisted that major operations required seizing a deep water port. Mulberry proved that wrong. The Allies had simply built their own, twice. Germany's fortified ports, once central to its defensive plans, were bypassed entirely. Engineering, not firepower, became the decisive factor. The concept reshaped post-war amphibious planning. Modern floating piers, modular causeways, and expeditionary harbor systems all trace their lineage to the Mulberries. Arromanches continued operating until November 1944, far beyond the 3 months expected. And today, at low tide, the silhouettes of Phoenix caissons still lie offshore, silent, immovable reminders of the moment when Churchill's impossible idea became a logistical miracle that helped win the war.